Okay, very good. So maybe we can get started. It's welcome to the third week of the conference. Is someone here just arrived? Miguel? Only Miguel? Okay, so we'll tell Miguel in private about the vouchers. No point in making the whole speech just for Miguel. So just one thing. So as you saw in the email that I sent yesterday, if you want to lead an informal discussion, it doesn't need to be a talk about something you're working on, but it can also be if you want to discuss whatever you want to discuss and suggest that we meet to discuss. Just let me know a time slot that is still free on the schedule, and we can meet in floor -1 at the other building in the afternoon. As you see, there are already a few talks there. And of course, these talks are not part of the regular schedule in the sense that no one is forced to. We are expecting that the specialists on a given topic will go to the talk on that topic, but these are more informal and perhaps more technical and talks on the other building. So yeah, do feel free to suggest more topics and to volunteer to either lead or to speak. And it's a great pleasure to have Yin Chen give us the second mini course of this workshop on fuzzy sphere regularizations of three-dimensional conformal field theories. Okay.
Yeah. First of all, I would like to thank the organizers for putting together this wonderful conference, and also thanks for having me. So today I'm going to talk about. It says on.
It says on. So maybe make it closer to you.
Okay.
No, I think they will adapt the volume.
Okay, so it's a topic that we actually came out last October, but I feel very excited about it, and that's why I would like to share the story with you to get more inspirations. So before telling you about what's the outline of these lectures, let me first give you some motivations that why we want to do this. So the general motivation is to study d-dimensional CFT, right, on the cylinder geometry, that is SD-1 times R, that I guess everyone should be familiar, that on the cylinder, so we have this as a time direction, and then we call it tau, and we can put your so you can consider, let's say, a quantum, the CFT, a quantum version, and then you put the space on the sphere SD-1, and then you will have very nice interpretation for this radial quantization or state-operator correspondence. So in specific, you can consider quantum Hamiltonian that defines on sphere, and then the eigenstate, both ground state and excited state, will be one-to-one correspond to the CFT scaling operators. Then making use of that, you can explore a lot of important information of CFT. You can more generally make use of this geometry to understand a lot of properties of CFT, and that will be this lecture is about. And of course, if you want to do some perturbative RG type of thing, there's no obstacle for you to put it on any geometry. But if you want to study it non-perturbatively, for example, you want to put it on a lattice and do simulations, then there will be it will be very difficult to put it on sphere as long as you are not considering 2D CFT. For 2D CFT, it's very straightforward that you just need to put your space on a circle, and then that's it. But for higher dimensions, because the sphere has a curvature, then you are not able to put a regular lattice layer. You may have to put some defect. You have to go with the lattice with a lot of defect, and eventually you may not get the CFT you want to study with. And for us, it turns out that the way out is not to consider a regular geometry. Instead, is to consider the so-called non-commutative geometry. So different from the regular geometry, the non-commutative geometry is a geometry that its coordinates are not commuting. So generally, if you consider just non-commutative Euclidean or RD, then you can define a commutation relation like this. And this epsilon ij is just some antisymmetric tensor. And theta is a number that characterizes this non-commutativity. So, this may remind you the uncertainty principle of quantum mechanics, where due to this non-commuting relation, then as a consequence, you are not able to precisely determine the position of a point on an operator. And that's why sometimes people call it fuzzy geometry. And for the fuzzy sphere, it's really that, so I'm talking about, let's say, 3D fuzzy 2 sphere, then the commutation relation is really just that I have those 3 coordinates of, on the fuzzy 2 sphere just follows the SO3 algebra. And again, this theta characterizes how fuzzy this geometry is. So, you will say, in the lecture, I will explain this. I will explain that why this fuzzy sphere eventually get around of this, how helps us to put 3-dimensional CFTs on the S2 times R. But before that, let me also say a little bit there's the non-commutative geometry. So in the end, with the help of the non-commutative geometry, we are able to realize this 3D CFTs on this sphere with 3 very interesting properties. One is that it's a model directly defined in the continuum. And secondly, it preserves all the space symmetry that is SO3 symmetry. So it's very different from a lattice regularization that in the end you have to make the space discrete. You end up with some discrete symmetry. And the third property is that it's UV finite. And that's how we are able to really put it in the computer to do the simulations. And looking at those 3 properties, you may think, that's what we are dreaming for regularizing a QFT, right? But of course, here, the price we need to pay is that we need to study a non-commutative geometry. And historically, the first person who came up with this non-commutative geometry idea was actually Heisenberg. You may not be too surprised to learn that, because this relation is really just some generalization of his uncertainty principle. And for him, the motivation was exactly to regularize QFTs. And that was, I think he came up with this idea before people come up with those normalization or regularization scheme. And in the QFT and the string community, maybe 3 or 2 decades ago, people also studied a topic very close that is called non-commutative field theory. That's really just you define a QFT on a non-commutative space. And there was a number of motivations, which I don't really understand. I think it comes from something like the defect of D-branes, and there you get this non-commutative field theory. So, I think our formulation is different from the non-commutative field theory. It's close related, but in the end, they are different. And you may know that the non-commutative field theory eventually suffers this so-called UV-IR mixing, such that you are not really in the IR, you may not end up with the QFT or CFT that you want to study at the beginning. But here, I don't think we have this issue. But I don't know the key difference, what really makes this difference. So yeah, we can, hopefully that we can discuss on this maybe later or offline to say whether this idea of regularizing QFT using non-commutative geometry can be really pushed forward. All right, this is the outline of my lectures. So in day one, I will just give you the general formulations that how we set up this problem, and in particular, I will just I will focus on our favorite CFT, that's 3D dimensional Ising CFT, and to formulate this fuzzy sphere regularization. And I may also give you some results about of our by using this regularization scheme. So in particular, I will try to give you two perspectives about how to understand this fuzzy sphere regularization. The first perspective is will be more familiar to QFT people, although I'm at the moment I'm not able to give you a very rigorous state proof that why it works. And then the second perspective will be more motivated from condensed matter side. There we know what we are doing and why we end up with the CFT we want to study. Okay, and in day two, I will then move to so about further applications of this scheme. In particular, I will talk about how do we study operators there. For example, how do we study OPE coefficients, and how do we study 4-point correlators. And then I will also talk about how to study conformal defect, either line defect or plane defect in this setup. And day three, I will talk about some generalizations. For example, how to generalize it to other CFTs, such as Owen, Wilson, Fisher. And then I will, in particular, focus on how to generalize it to gauge series, like Dirac fermions coupled with gauge field. And for example, we can consider SU2 gauge field coupled with n flavors of Dirac fermions, and how to realize it using this fuzzy sphere regularization. So, any questions? A moment. All right. So, yeah. Also, I think I should mention that the idea of fuzzy sphere was first proposed by Mado. I may not pronounce his name correctly, in 1982. Okay, so let me give you the first perspective of this fuzzy sphere regularization. So as I said, we want to consider CFT on the cylinder geometry, and in specific, we want to have a Hamiltonian on S2 that realize the CFT, realize the 3D Ising CFT. Okay, so then let's say we just start with a sphere, right? And then the first step, and what we are going to consider is that we are going to put electrons that is moving on the sphere. And the electrons will be non-relativistic electrons. So doesn't have to have Lorentz symmetry. So that means you don't need to, we don't consider Dirac spinors. But we will have it, but the fermions will have two flavors. It's really just a flavor symmetries. Don't confuse with it with like the spinor indices. It's with two flavors that called spin up and spin down. With that, they move on the sphere, right? And then we can have an Ising Z2 symmetry. X on those fermions, it's just X Vermilion way that we have it spin up goes to spin down and vice versa. Okay, And of course, you can write it more compactly. Let's say we have and then this Z2 symmetry just maps. Yeah. So from those electrons, then we can just build up spin operators, like Ising spin operators. So that well looks like the density operators.
I miss the meaning of this dagger that you have or this plus that you have.
Sorry, you mean the sigma? Or?
No, you have a dagger, a plus, or what? What is it?
Dagger is creation, right?
Okay, so you already are in doing modes. These are not fields.
You can think them as operators. That if you that are not fields. Then, yeah.
Okay.
So you can define spin operators as the density of those fermions. Those sigma A, just Pauli matrices. You can also put identity there, which I will call N0. Okay, so having those operators at hand, we can write down and you may quickly realize that let's say for NZ, it will go to minus NZ. That's also the case for NY under this Ising Z2 symmetry, right? NX is NX, and N0 will be unchanged under the Ising Z2 symmetry. So with those operators, you can quickly write down schematically write down a Hamiltonian that's a realized quantum Ising models. So let's say we So we can write down some model like this. And the first term, you can think it as just the conventional Ising interactions that put on a sphere. And the second term will be the so-called transverse field that can disorder this Ising ferromagnetic order. So this U will be just some interactions. For example, you can take U as some local interactions, such as just delta potential. You can also put, let's say, Laplacian delta there, all those things. It's just some interactions. So you can easily convince yourself that, let's say, if we don't have this transverse field, right, the first term may favor the spontaneous break the Z2 symmetry, such that I end up with this Ising.
Sorry, I hate to ask because probably this is very elementary and very standard in the condensed matter literature, but normally we think of the Ising model as a theory which has some elementary bosonic degrees of freedom with a Z2 symmetry. So somehow it seems to me that the really crucial step here is you're rewriting that as a composite in terms of some fermions. And okay, where does that come from? Because if you want to generalize to some other system, what's the idea?
So,
what's the intuition?
Yeah, so you will say this from this second perspective, that the model really comes from this so-called quantum Hall system. There it comes with electrons, right? Yeah. And, but you know, even for, let's say you consider the conventional, let's say, a lattice model of spins, right? You know, usually in the real world, those spins comes from electrons, right? So deep down, it's an electronic model. Yeah.
No, but this is still interesting. So, for example, we are familiar with the transverse field Ising model where you have just immobile spins and they have a very similar Hamiltonian to the one that you're writing.
Yeah.
Now we have two possibilities. A priori, we have two possibilities. Possibility number one, you just say I promote each spin in this transverse field Ising model to some bosonic field which is going to move on the sphere.
Yeah.
And here, you did not discuss this possibility. You went straight to this other possibility where you don't promote bosonic fields to bosonic spins to moving objects, but you decompose them in terms of fermions, and it's fermions which are moving.
Yeah.
Can you comment why, like this even more naive attempt, delocalizing bosonic spins would not work?
Okay, so I think if you just do the naive one, then you will end up with non-commutative field theory. That's really
non-commutative.
Because we know it won't work. In the past study of the non-commutative field theory, you may end up with IR.
No, why non-commutative? For the moment, everything is commutative. I just promote spins.
Because here, so here, there's no problem for you to do so. But in the end, we want to put it on the non-commutative space.
I don't know why.
Right.
Why do you want to put it on the commutative space? Is it like a game in itself? I mean, why do I care?
You will see. You will see. This is a continuum model. Once we write it down, we still cannot really properly define it.
What if I just do simple things? I do just bosonic spins moving on the sphere. Does it do anything interesting, or is it just like totally wrong?
There may be different versions of it. So let's say, do you want to, let's say, replace those sides with bosons, but then the spin operator is still the composite operator? Is that the approach you want to do, or you just directly want to have spins?
The most naive would be directly do not composite, no compositeness.
So, but in the end, you have to deal with this continuum space, right? The question is how do you deal with it, right? Maybe it's
okay. Maybe it's premature.
Maybe it will become more
But in the end, it would be interesting. Like, okay, you're not just going to describe some fairly complicated construction, and in the end, it would be interesting to know, like, whether all the choices you made are forced. Whether if you do something simpler than that, it just wouldn't work.
I don't know, but I don't know. That would be this way. Yeah.
Can I just ask something? Is it fair to say that the fermions are there to sort of create the fuzziness of the geometry on which you then consider different operators?
Yeah. In the context of this fuzzy sphere regularization, it will become very clear that why we want to use fermions to construct spin operators. But I think it doesn't completely answer Slava's question that why do you want to start? So forget about this fuzzy business that's just do bosonic spins on the sphere. Whether this would work or not? Yeah, that I don't know.
I have a kind of similar question, but let me kind of phrase it in the following way. So the Hamiltonian, this thing is, do you have to do some tuning? Did you include all the terms that's needed?
We need to tune the system into the phase transition, right?
Which parameters are you tuning here?
So here, I will be more concrete on what's the precise Hamiltonian I want to study and how to tune it. But here you can think that, let's say if we don't have this transverse field, then I will get spontaneous C2 symmetry breaking. If this transverse field is strong enough, it will just polarize the spins such that it's C2 preserving, and in between I will get a phase transition. That's the parameter.
But in this U itself, you don't have to.
In the end, we also tune it a little bit. Yeah.
So it's not going
it's
to
like
be exactly this
double
function
tuning
you
in
wrote
our
here.
story. Yeah.
I mean, here you wrote the specific distribution. You're saying that needs to be modified?
Sorry again?
The U here, you wrote a specific distribution. Are you saying this
Okay,
will be
let
modified?
me put a parameter here. Okay, G.
Okay.
Yeah. All right, so as I said, in this Hamiltonian with some tuning, then naively you can realize this 2 plus 1D Ising transitions on a sphere. But here, with this problem, you cannot really solve it because we know it's a continuum model, then it will be UV divergent, right? So you have to deal with it first before really do any computation, right? To say the UV divergence, one way to say it is that, I mean, the reason that you get UV divergence is really just because you can have infinite number of angular momentums, and then that will cause the UV divergence.
I'm sorry, I'm confused. Why do you divergence? Why can't we just consider this model in the sector of n electrons, which regulates UV divergence?
Sorry, I missed the...
So we have this fermion operators, right?
Yeah.
But we can consider now occupation number, how many fermions we have in the system, and we just restrict to this Hamiltonian to the sector of n fixed number of fermions.
Yeah.
Would that be okay?
I will explain how to, if you want to play with this model, how to deal with it.
Yeah, but I just don't understand why you say there are UV divergence. There's no UV divergence. If I restrict...
You need to, let's say, you need, there are infinite number of angular momentum. Let's say, it's just like the QFT that you consider in the momentum space, then the momentum, the infinite number of momentums, and so on.
But the Hilbert space is finite.
No. Here,
why not?
It's a continuum, right? If you want to define Fock space, you need to go to the momentum space or angular momentum space. There you get infinite number of momentum, or angular momentum.
So, but here you don't consider a kinetic term for the fermions themselves. It's only this composite.
Right. For this model, we. So yeah, I have to say it's a schematic model. Then let me put it this way. Yeah. I just try to give you some flavor about how to do it. Yeah. You can put kinetic term to the fermions. So we can so let's say we can decompose those fermion operators in the angular momentum space, right? So let's say just put some normalization here in order to make the dimension right. So you can, let's say, expand the fermion operators in the real space into the angular momentum space, right? That's a bit like what you're doing in the QFT, that you expand the field in the momentum space. Okay, now you say that there are like infinite number of angular momentums, and that's the source of the UV divergence. And so like QFT, what you would normally do is that, let's say, we have a truncation, right, in the moment, for the momentum, and then that will be UV finite, and then you you carefully take the momentum goes to infinite limit, right? Here you...
Sorry, I have some basic confusion.
Yeah.
What happened? Sorry. Here you're still on the plane?
on the sphere.
Okay, so
Yeah, that's why I'm using
fixed
spherical.
R. Okay.
Yeah, using spherical harmonics and expanded in the angular, associated angular momentum.
Okay, so these integrals over R, they're really integrals on the sphere?
Yeah, they're integrals on the sphere. Yeah. So then, yeah, the normal way of doing it is that that's just a truncate. It has some angular momentum, and then you carefully take the L goes to infinity limit, right? Whether this way of treating it will work, I don't know, but what we are going to do is do this so-called fuzzy sphere regularization, and then so you can understand it as the following. So here we still start with this spherical modes expansion, but we're not going to use spherical harmonics. Instead, we are going to use monopole harmonics, also called the monopole harmonics, also called spin-weighted spherical harmonics. I will just write it as this. And this, you may know that the 2s, the s should be integer or half integer. And here L, the SO3 angular momentum should be no smaller than s. So that means it will take values starting from s, s plus 1, and so on. That's the so-called monopole harmonics. You know, it's indeed just a solution of the case that of angular momentum in the presence of these monopoles. And you know, originally that in physics context that was first probably studied by Wu and Yang in their famous Wu-Yang monopole paper. So I will later I will just explain that these monopole harmonics are really just the single particle states of the so-called lambda levels on sphere. I will come back to this later. But let me first, so this monopole harmonics has, of course you can, indeed you can write it down. I'm just writing it down, but you don't really need to memorize it or even read it. So I just write it down showing that it's not super complicated. And the compact form of it exists. Okay, it's barely enough. It's theta. Phi only appears here. It's like this LZ of the SO3, right? It's basically similar to the spherical harmonics. So there are few properties of monopole harmonics worth noting. The first thing is that. Oh yeah, thanks. First of all, if s equal to 0, then monopole harmonics is really just spherical harmonics. And secondly, is that monopole harmonics, just like spherical harmonics, also is, let's say if you pick a specific L, it will be a spin L irrep L of SO3. That's the same as the spherical harmonics, but the only difference is that L can only taking values starting from S, not from 0. And the third thing is that for any S, the spherical, the monopole harmonics is a complete orthogonal basis. So just like the monopole harmonics. So sorry, just like the spherical harmonics. So then you can just say, okay, in this standard treatment, why don't, so we are free to choose either spherical harmonics or just all the monopole harmonics, right? Now let's say we can choose monopole harmonics, right? And then we have this expansion and then we do truncation, right? That is, that's a starting point of the fuzzy sphere regularization. And, but the key step of the fuzzy sphere regularization is that now I'm expand those modes using multiple harmonics, and I'm doing a very do a very simple truncation that say we just truncate it at the lowest order. So instead of that, we truncate it with very high order and push it to infinity. And we truncate it at lowest order, and then we take S goes to infinity. And then we say that's the thermodynamic limit we want to study. So technically, that's what this fuzzy sphere regularization about. We take S goes to infinity. That corresponds to we have infinite large physical volume. That's what I claim that gives me the thermodynamic limit, let's say, of the 3D ISXFT I want to study.
Okay, sorry, maybe it's a matter of language, but I thought the volume is finite because you're on a sphere. And that corresponds to removing the UV regulator.
If S goes to infinity, then the volume is infinite, right? The volume is basically like how many electrons or how many states you have, right?
Okay, I'll think about it. But I thought we're on S2 times R.
Yeah.
The volume is finite, or the spatial volume is finite. It's a matter of how many degrees of freedom we have, which is removing the UV regulator.
Yeah, you can think it that way, that we remove the UV regulator. Let's say if you think it in terms of lattice, then we are pushing the lattice space into zero. You can think it that way. Yeah, but yeah, this in our community, that's what we usually call the infinite physical volume. Yeah.
A question on this monopole harmonics. The usual spherical harmonics you get from solving a differential equation, like Laplace equation on the sphere. What do these satisfy instead?
That's still the Laplacian equation, but with the presence of monopole. Right? Sorry, I didn't understand. With the presence of monopole, then you modify the Hamiltonian by adding the minimal coupling of due to the gauge field. That's the. Yeah.
Okay.
Yeah, the S is a monopole charge. Yeah. Yeah. No, it doesn't. It starts with S. Yeah. So, so by taking S goes to infinity, then so from this perspective, it's not obvious at all that why in the end, when S goes to infinity, I can get the right answer that I want, right? But at least it meets the minimal requirement that I really have infinite number of states. If S goes to infinity, that probably means at least it might be able to produce the right physics in the continuum limit. Yeah, that's true. There is no guarantee that why this works. That's why at the beginning I would say this perspective is not rigorous. I don't know how to make a very clean statement that why we can end up with the CFT we want to study. But this perspective might be more familiar with the QFT treatment, right? Like we expand the modes in the angular momentum, and then we do
Maybe this is just an elementary confusion, but I would have thought we should keep the small angular momentum modes.
Yeah, that's why we keep the smallest one.
But
Right.
you said that L bigger than S is what appears, not L smaller than S.
Because they just don't exist, right? Due to the monopole.
Okay.
Yeah. L equals to S is the minimal angular momentum you can have mathematically.
I guess the point is that this is no longer the same L, right? It's not the quantum number of the same operator.
No, it's not.
Right, so-
Right, it's not. Yeah. But still, I mean, but still the SO3 angular momentum in the end. Yeah. That's in the presence of monopole, then you need to modify those operators with the gauge field, right? That's that.
Sorry. Maybe it's a detour, but why are we discussing monopoles at some?
That's how you get fuzzy. Yes. Yeah. Yeah. So.
Sorry, just to be clear, usually we think of the sphere harmonics as a basis for scalar functions, just ordinary function on a sphere, but these monoharmonics are a basis of not functions, but a section of a vector bundle, in the case, a line bundle over the sphere. There's a different bundle, right? So if you, they're not exactly on the same footing. If you expand the ordinary function in terms of this, they will have some weird singularity naively, right? I mean,
No, it doesn't have. In the end, it gives you non-commutative.
No, I'm just saying that the sphere harmonic. I mean, these are supposed to be a section of some non-trivial bundle over the sphere. So if you write two patches on covering northern and southern hemisphere, the gluing condition is different. So maybe you are secretly changing the kinetic term in such a way that.
I'm not entirely sure, but it might be related to that. In the end, we just get non-commutative coordinates, which I will explain in a minute.
Sorry, you explained, so this is your truncation scheme.
Yeah, that's my truncation scheme.
So it surprisingly works. So you don't
Right. From this perspective, but in the second perspective, when I explain physics, the story in terms of those condensed matter language, like quantum Hall physics and so on, that's what people are doing for decades to study.
So you are saying basically this truncation naturally coming from some condensed matter system, so that you got that intuition borrowed from there.
Yeah. But after you understand technically, that's what we are doing.
Sorry, I thought a crucial idea, maybe it'll come later, is that unlike ordinary harmonics, whose product is not closed for a fixed truncation because you get higher harmonics, the point here, you're deforming the algebra of functions such that for a given truncation, the algebra closes. I thought that must be an absolutely essential point of what you're doing. The product of two harmonics of spin L gives you spin up to 2L. But for non-commutative harmonics, that's not true. There's a truncation there's an exact truncation that only involves spin smaller than L.
Yeah. I think
somehow that must be the essence of your talk.
Yeah, probably right. But at the moment, I'm not able to make any.
Oh, these are not the fuzzy harmonics?
I think they are.
They must be. I mean.
Sorry, let's use the mic. Can you pass?
They're closely related, but they're not exactly these functions. So when he truncates at S at the lowest level, he gets like 2s plus 1 squared functions, and these are then rearranged into an algebra of 2s plus 1 times 2s plus 1 matrices.
yeah, maybe we can check this offline. So I think you're probably right, but yeah, I'm not able to make a clear statement on what you said. So technically, that's that's really what we are doing, right? And it's not unclear why, in the end, this approach gives me the right physics. But it will become clear in the perspective too that if you just think about this model, this precision in the condensed matter language, that quantum Hall states on the lowest order level and so on. So before going to that, let me also say a quick word that why this, in the end, this truncation scheme in the end give me the so-called fuzzy sphere, which follows this commutation relation. So the thing is, we can consider, let's say, we just consider a point on the unit sphere, right? Just consider this guy. And then you project to this using this scheme, right? So then for this coordinates, what you end up with will be 2s plus 1 times 2s plus 1 matrix, right? You just do a simple projection. Here, this omega is just the theta and phi that we use to label the coordinates on the sphere. If you do this computation, then you will find that they just follow this the SO3 algebra. And it's and its norm looks like this. So yeah, it's a straightforward computation that you can do it with Mathematica. So that's why we end up with this fuzzy sphere. And one thing you may notice is that if I take s goes to infinity, this fuzziness is gone, and I recover the unit sphere as well.
So can I ask a question?
Yeah.
Is there a version of this deformation of the spherical harmonics that would apply for vector spherical harmonics? So that we could just implement this truncation procedure directly on the bosonic degrees of freedom instead of so avoiding to have to go through this making them composite and so on.
I'm not entirely sure I get your question. So you're asking if you just use spherical harmonics? Or?
Let's decompose the n field
yeah.
in vector spherical harmonics.
Yeah.
I'm asking if there's a deformation of vector spherical harmonics similar to this one.
What's the...
Use the microphone, yeah. If you want to say something.
I mean, you need to expand a vector in vector spherical harmonics. You need 3 components. You need to expand a field that has 3 components, not 2, in order to expand it in the vector spherical harmonics. Yeah. So S should be taking 3 in the 3 values, not 2.
Sorry, another question. How is this bracket defined?
Sorry?
How is this bracket defined?
You end up with 2 matrices, right? Then you just
matrices,
the
okay.
commutation of those 2 matrices. So not entirely sure I understand your.
I mean, you just went from one complete set of functions to a different complete set of functions.
Yeah.
Started off with complete functions.
And by vector
We started with the complete
harmonics,
basis of scalar spherical harmonics, and you deformed them into this family labeled by this S parameter. I'm asking for vector spherical harmonics.
So what is vector spherical harmonics?
It's a complete basis for vectors.
Okay.
If you want to decompose a vector on the sphere, you have to use a different basis.
Okay. It's not spherical harmonics, not monoharmonics, right?
It's vector. It's similar to the scalar spherical harmonics, but
okay. Yeah,
so there is an analog of this deformation. So in principle, you could have just done it directly for these n's instead of.
You could have, but I don't want to steal his punchline. If you did that, then you get the wrong result. Because of this UV-IR mixing, which he's going to get into.
Yeah, there should be a deep reason that why this approach works, but I don't know that reason. Right? Yeah. But all the inspirations that why we want to do this, why this works, really comes from the physics of Landau levels, quantum Hall physics that we condensed matter are dealing for decades. Yeah. All right, so let me go to perspective 2. Yeah.
Point out kind of a very basic thing. It seems that all your y, s, l, m, they all vanish at theta equals 0 with degree at least s. So that's the thing I was saying about the singularity. So I guess it's kind of a weird thing to expand scalar functions on the spaces. I mean, I can believe that.
It doesn't vanish.
No,
they vanish.
Yeah, they vanish at degree at least s.
At theta equals to,
yeah. So. It's kind of a weird thing. I guess with back to some suitable L2 norm, it can be a complete basis, but somehow all these functions vanish at one point. That's kind of singularity I was referring to. It's kind of a weird thing to do for a scalar function, because these are supposed to be a basis for functions of a wave function of a charged particle, not supposed to be an uncharged particle. But
probably for one function it's not vanishes because I have.
No, it is. You can take the term with m equals L minus. Anyway.
Yeah, we can check. Yeah, I think there's one function that doesn't vanish, but that's confirmed offline. Yeah. Okay. So now let's go to the perspective 2, where you would understand, or I would justify that why this treatment, this would in the end give me a physical theory in the thermodynamic limit. So let me now just start with just 2D flat space instead of this spherical space. So let's just remind ourselves about some basic physics of this Landau levels and also quantum Halls. So let's say we start with 2D flat space that I have electrons moving in the presence of a magnetic field that is perpendicular to my space, right? I have a magnetic field, and then I have electrons moving in this. So we know that, then you can write down its Hamiltonian just in terms of canonical momentum and also the gauge field. That's really just the minimal coupling. So then you can solve this Hamiltonian. It should be some quantum mechanical problem that we did when we were undergraduate students. And then solving it, you will find that it's eigenvalues, its eigenstates will just form complete flat lambda levels, that complete flat band that we called lambda levels, right? And each and the energies for those lambda levels will be omega n plus 1. N is really just the lambda orbitals. Omega b is this so-called cyclotron frequency, which is one of the characteristic scale or number in this lambda level problem. Okay, so and a very important feature of those lambda levels is that each flat lambda levels indeed contains a massive number of states. So the number of the states in each lambda level, which I will call an orbital, will be like this. This phi 0 is just a flux quanta, like this. So L is just L squared, just the area of this space, and the number of this. So you can say that each lambda levels have a very massive number of degeneracies. So then you can consider a Hamiltonian. So this is just really a free Hamiltonian. Then what you can do is that we can add interactions, right, to this Hamiltonian, right? So then let's say that's the Hamiltonian that describing electrons moving in this 2D plane with the presence of magnetic field, right? This interaction Hamiltonian is basically the Hamiltonian that I wrote like there. So then if you consider a situation that, so first of all, in this system, the thing that you would realize that, say, if you take physical volume to be infinite, that corresponds to you take, I should first say that let's say you consider the situation that, let's say I have a number of electrons, which is smaller than this n orbital, right? So then energetically, those electrons will be favored to stay in this lowest lambda level, right? So then if the interaction scale is much smaller than the gap between different lambda levels, right? Then I can mathematically just project this Hamiltonian into the lowest lambda level, right? Without really changing anything, right? That is what we call lowest lambda level projection. So it's really just a trick that make your life easier, right? We can understand the eigenstates or energies of this interaction Hamiltonian by just projecting this Hamiltonian into the lowest lambda level, right? And the other thing that you may recognize is that now in this setup, if I take L goes to infinity limit, that corresponds to the thermodynamic limit, right? It's really I take this number of electrons to be infinite, right? So after you project it to the lowest lambda level, that becomes equivalent. That's the only physical volume that you can have in the system. So that's we call lowest lambda level projection, and in the context of quantum Hall physics. So now you can now we just go back to the sphere, right? Now the thing is we now consider electrons moving, let's say, on my sphere, right, in the presence of 2 pi S monopole, putting on the center of the sphere, right? So then my Hamiltonian will basically something like this. I will have, let me also use capital M here. And plus some interactions. The interaction will be just the form that I wrote there. So this, the first term is really just the kinetic energy of my electrons moving on the sphere, right? So yeah, that's really just the minimal coupling there. So then you can similar as this lambda levels on the flat space. You can solve this. You can first look at the first term, then solve this quantum mechanical problem. Then in the end, you will end up with the so-called spherical lambda levels, and the spherical lambda levels will have energy slightly different from this guy. Will be but the point is still quantized, and for each lambda levels, the degeneracy will be and most crucially, the wave functions of these lambda levels in this problem then will be just my spherical harmonics. So then this really tells me that what I was doing here, that what the problem that I'm really consider was that I have electrons moving on the sphere in the presence of this monopole, and the electrons can interact with some Hamiltonians, like what I wrote there. And then I consider a limit that the interactions are much smaller than my gaps between lambda levels, such that mathematically I can just project it to the lowest lambda level without changing anything, right? And this tells us that why we want to play with multiple harmonics, right? And it also tells us that why I'm doing truncation at the lowest order. And this also tells us the thermodynamic limit, right? As I explained here, so from this relation, you can say that if you take the physical volume to infinity in this lowest lambda level problem, is just equivalent to the number of states on the lowest lambda level goes to infinity, right? And here it will then just correspond to this S goes to infinity. That's why that justifies that why we do this treatment, and then why in the end it gives me a theory, a right physical theory at the S goes to infinity limit. So then this.
Ask a question. So can I think that physically, so the electrons are equally spaced on the sphere because of some bare Hamiltonian, and then on top of this uniform distribution, I now start putting small interactions. And then I don't care about the bare Hamiltonian because all it does, it puts the electrons uniformly spaced, right? And then was it important that it was this particular Hamiltonian with a monopole, or could I just put fermions with a small repulsion and it would do the same? Or what's the criterion that, why this particular mechanism to spread the electrons on the sphere and not another mechanism? Or?
Because you need a way to separate the electrons staying here from the states from here from other states, right? That's a bit like truncation, right?
Okay.
Yeah.
So can you remind just qualitatively? So if you fill the first Landau level, they are uniformly distributed on the sphere.
Yeah.
And if I go to the first? How should I think? What's happening if I put the electrons on the first level instead of the lowest level?
You still get the electrons distributing there, right? The thing is, we want to deal with UV finite system, right? So then we cannot include all the states in the system, right? I want to truncate at somewhere, say that's all this Fock space, or that's all the space I want to consider, right? But then to justify that truncation is really physical, here what we have is that due to the presence of magnetic field, there's a gap between each band or each lambda levels, right? And then the thing is that I'm free so I have two scale. One scale is this lambda level gap. The other scale is interactions. The thing is I can push this scale to infinity without changing this guy. So that's why that in the end, this truncation is entirely physical. Yeah, I can separate this scale, these two scales. I guess that's the one key point.
So these energies and degeneracies are valid for the limit of no self-interactions of the fermions, right? Or just interactions with the monopole?
Sorry.
On the sphere,
yeah,
these energy levels and degeneracies are in the absence of interactions. So
right. They are in the absence of interactions. Yeah. So yeah, I feel I'm running a little bit late. So that's the perspective two, that how we understand this truncation.
Yeah, so I guess there is some piece of information here that you are not really explaining to us. So if the magnetic field is zero, then we're kind of dealing with the previous model. We know that it should realize the Ising transition, but there is an infinite number of states, so it's not good.
Yeah.
Now we start turning on this magnetic field. And so we start decoupling. These levels are going higher and higher up.
Yeah.
So there is some implicit assumption here that there is some critical magnetic field beyond which physics completely changed. So you claim that even in the limit of very large magnetic fields, well, all these states are completely decoupled, you're just left with the lowest lambda level, you are claiming that the physics does not change.
No.
So where does this follow from?
Yeah. So first of all, it's unclear whether this guy really realized the 3D Ising transition, right? It just intuitively think it might, but to really address that question, you need to first define the problem properly, like, for example, do some truncation and so on, then study it, right? And here I'm just trying to give an intuition that this type of Hamiltonian may capture the 3D Ising transition.
Well, if at all, it should capture it better than this one. This one is a total...
This one, I don't even know how to deal with it, right? So then I'm not... Right. So, but here, as I will explain, that so here to realize the Ising transition, it's...
Why should it realize the Ising transition?
Yeah, I will explain.
Okay.
Yeah. So that's basically what this fuzzy sphere regularization about, right? So the actual physical problem that we are considering is a problem that with interactions in the presence of magnetic monopole placed in the sphere, right? But and in condensed matter literature, that's really just the physics on the lowest lambda level and so on. So now let's go to the 3D Ising transitions. So the Hamiltonian that we are going to consider is really just this guy with the interaction there. So let me give you a physical picture that what does this, how to think about these phase transitions. So first of all, we can just write down the Hamiltonian in the orbital basis, right? That's really just the basis of this monopole harmonics, right? So in condensed matter literature, that we usually call it lambda orbitals. So just remind you that we will have in total like 2s plus 1 orbitals, right? And pictorially, you can just view those orbitals as a lattice site, right? So that's where our Fock space defines on. So now we have electrons moving on this, right? In this system, and in other words, electrons, you can just view them as lattice site. Then we have electrons moving at those lattice sites, right? And at each orbital, I should be able to write, I have 4 states, right? Now I'm using the second quantized form for those electrons. M is just the orbital indices. The spin up and spin down are just my flavor indices. I do have those. In each orbital, I can have those 4 states, right? And so then also let me write down the how to relate my Fermi operators on the real space, whereas those operators defined on the Fock space. Okay, so now so we want to study the Eisen transition, right? So then we want to ask what are the states of the what are the Z2 symmetry breaking state, and what is this Z2 preserving state, right? There's a very simple. So in this orbital space, those 2 states are basically the Z2 breaking state will then be just that I have all the spins on each orbitals to be either plus or minus. Right. Those are my Z2 breaking states, right? It's a bit just like the Z2 breaking state on a 1D chain. And Z2 preserving state will be
Is there a half filling constraint?
Yeah, it's a half fill. Yeah. Thanks for the Z2 preserving state will be just this guy. So then by tuning the parameter like transverse field, then we can tune the transition between those two. And that's how we realize this 3D Eisen transition. And in the condensed matter context, such state, for example, this Z2 breaking state are called quantum Hall ferromagnet that has been also observed in experiments. So, and pictorially, the state is in the orbital space is really very easy to understand. That's really just a product state that occupy on each orbitals. You have 1 electrons, and its spin polarizations was pointing to either up or down directions that spontaneously break the Z2 symmetry.
Sorry, these are definitions of states, or these I didn't understand what these equations are, the last equations. Are they definitions or they
you
are...
mean here?
That I understood. It's at each orbital you can either put one electron or two or nothing. That I also understood. That was explained before. And the last part. Is this a definition or what is this?
The many-body ground state of the Z2 breaking state and also Z2 preserving state corresponding to H equal to 0 limit and H goes to infinity limit.
Okay, that was what I missed. Okay.
Yeah, that's the order disorder.
So when H goes to 0 and infinity, those are the ground states.
Yeah.
I see. Okay.
We can easily work out this indeed.
These are the actual states, or you are saying that this is representing the symmetry breaking and non-breaking states? There should be corrections due to interaction or whatever.
Yeah, at the extreme limit, then that's the true ground state. Okay. So here correspond to H equal to 0. Here is H goes to infinity.
I see.
In this limit, then that's the exact ground state of the Hamiltonian.
The restriction on half filling, that's just part of the definition of this regularization?
Yeah, that's a part definition of the problem. Yeah. You can kind of say this, if I'm at half filling, then I can have this product state. Otherwise, then I'm running into trouble. Yeah, I think so. Yeah.
We had lots of questions. Is there any other question before the break? Otherwise, we can continue to ask informally. Okay, so let's keep discussing during the break, and let's resume at 11:15. Okay, now this is more clear.